successful performance of a building is measured in terms of comfort, pleasant atmosphere, and sustainability. Current architecture trends is heading towards the direction of dynamic and adaptive building envelopes for responding to external and internal changes in climate and user behavior. The focus of this study will be mainly on implementing different design strategies for reaching optimal building performance by using the least possible amount of energy to maintain building interior comfort for occupants while maintaining aesthetics and pleasant appearance of the building. Hence, the office building spaces would improve occupants' performance during work hours as they reach the optimal space comfort. The aim of the study is to achieve design sustainability using energy analysis, kinetic architecture, and implementing renewable energy to the building. The chosen location of the site is in Canada, Toronto City, in the capital of Ontario, which lays on the northern shore of Lake Ontario. Toronto City has many iconic buildings and famous landmarks, such as the iconic CN Tower, Art Gallery of Ontario, the Casa Loma, Royal Ontario Museum, Ontario Science Centre, and many green areas, famous parks, and natural tourism destinations. The chosen site is located in an area where it's accessible by 12 meters main street and a 9 meters branch streets. It is also surrounded by 1 and 2 story commercial buildings, empty lands, green area, and residential area. In addition to several service facilities like schools, parks within the distance of 1 kilometer, stores, and bus stops within the distance of 700 meters. According to the LEED assessment, this would help us earn more points. The climate in Toronto City is temperate climate with extremely cold winters and warm summers. It has all 4 seasons, yet the climate is affected by the outbreak of polar air masses coming from the North American continent. As shown in the map, some path in Toronto has the lowest altitude in December and the highest in July. The diagram displays the wind direction throughout the whole year. Prevailing wind direction is mostly from the west. The highest temperature range is in July and the lowest is in January. The basic design and material selection was done based on the minimum requirements of the National Building Code of Canada. Then it was upgraded by using suitable U-value materials according to Canada Green Building Codes. The U-value of the materials on the base case was reduced for the walls, windows, and roof. By looking at the table of the total energy consumption for the building, the optimum orientation determined by the least energy consumption, which was rotating north at 0 degrees. The design was developed by raising the height of part of the building and adding a skylight facing the south to increase solar gain for the winter and improving natural daylighting. As per energy consumption, in terms of heating loads, it was decreased by 17%. The facade shape was obtained from the pixel concept, and the movement was inspired by the wave motion, which is achieved by rotation mechanism done by a servo motor that rotates gears to control several square panels. The panels will rotate to follow the direction of sunlight on a vertical axis by two mechanisms, each panel rotating individually and complete axis rotation. Comparison will be conducted between the base case and the optimal case using thermal analysis, daylighting analysis, and airflow. According to the recorded temperatures of the city, scenario dates were chosen from the lowest and the highest recorded month temperatures. Suncast analysis shows the levels of sun exposure on the elevations of the building. The focus of the analysis will be on the southern elevation as it has the most sun exposure throughout the whole year, followed by the western and the eastern elevations. The northern facade has almost no sun exposure. Hence, the kinetic facade would be applied on the three south, west, and east elevations. As mentioned before, facade panels will be rotating according to weather conditions. In winter, it will be fully open on timings when the sun rays are directly facing the facade. In other facade, it will be open towards sun direction. In summer, it will be partly open in south and west facades to protect from excessive heat gain, whilst admitting natural daylight. Same will be applied in autumn according to weather conditions. Presented tables are showing an example of facade opening status in each scenario at 12 p.m. In winter scenario, an increase of building temperature and solar gain is noticed in the optimal case when HVAC system is off, especially at 3 p.m. Daylighting was decreased significantly for closed offices, yet it's still within the standard lux value for offices, as shown in the contour pictures for lux value. Displayed psychrometric chart is showing the improvement in moving building spaces closer to the comfort zone. In summer scenario, air temperature and solar gain were reduced due to the shading of the facades, with up to 60% reduction in solar gain at 9 a.m. and in daylighting up to 63 degrees in average daylight factor and lux value. Lux contour shows optimal case daylighting is also within the range of standard lux. Psychrometric chart is showing the change in building spaces distance from the comfort zone. In autumn scenario, air temperature, solar gain, and daylighting was decreased while maintaining the thermal comfort and reaching greater comfort zone as shown in the psychrometric chart.